The basic parameters of the physical world, such as the constants of nature, seem accidental. However, in the bootstrap picture, the universe is a self-consistent whole, and therefore it should contain nothing accidental of a fundamental nature. We cannot distribute accidental properties in random combinations among universes in this picture, as in the anthropic principle, until better and more general theories are found. We should note that the anthropic principle is a makeshift or poor man's bootstrap. It existentially relates organisms and the universe, and although it is only a partial bootstrap, it nonetheless is useful until better ideas are found. When we receive a wild organism, we also receive our universe. Perhaps in the future, when we receive an electron, we will also receive our universe. We will find heaven in a wild owl, an electron, or any other particle. Where in the universe is the cosmologist studying that universe? The physical universe successfully explains how various things work and lets us control our environment. But it fails to explain psychic things, such as consciousness and self-awareness. A person who persistently asks where life and mind are in the physical world will be passed from science to science as a person with a mysterious illness, passed from specialist to specialist. The biologists will say that life and mind are the manifestations of elaborate physical systems of billions of organized cells, and each cell is an organization of billions of atoms. If this answer fails to satisfy, the biologists will recommend visiting the psychologists. No two psychologists will give the same answer. Some will talk of mental processes of the mind. Others will talk of neurological processes of the brain. And others, admitting that they know very little about the physical universe, will recommend a visit to the physicists, who seem to be doing some pretty deep things these days. Physicists will deny the issue. What is not physical does not exist, or suggest seeing a biologist. In desperation, the inquirer might then think of consulting the cosmologists. Cosmologists, at least some, confess they do not have the foggiest notion of an answer. They know instead that universes come and go, springing from the imaginative fertility of the human mind, and they wonder whether a product of the mind can adequately explain the mind. The buck stops with the cosmologists because of the containment riddle. Where in a universe is the cosmologist studying that universe? Other scientists can avoid the riddle by claiming it does not belong to their province of special knowledge. But cosmologists study the universe, and the riddle stares them in the face. Consider a painter who paints a picture of his studio. The painter is inside the studio, but does not depict himself in the act of painting the picture. An attempt to portray the act of painting leads to the absurdity of an infinite regression of pictures. The picture contains the painter painting a picture, which contains the painter painting a picture, and so on indefinitely. The universe is a world picture, and the cosmologist is in the same situation as the painter. The cosmologist constructs a world picture that contains his physical body and physical brain, but not his mind that constructs the picture. Let's assume he does not exclude his mind or perceive himself solely as a physical brain. In that case, he also encounters the absurdity of an infinite regression. The universe contains the cosmologist studying a universe, which in turn contains the cosmologist studying a universe, and so on, indefinitely. Where, then, is the cosmologist studying the universe? Can an image contain the image maker? The physical universe, consisting of multiple uses of facts woven together in a web of ideas, does not contain the thing that shapes the facts and spins the ideas. The containment riddle must be answered by those who cannot agree and assert that life and mind are merely a collective dance of atoms. Generally, those who think that life and mind are fully contained in the physical universe confuse it with the unknown universe and mistake the mask for the face. The containment riddle applies to universes of all kinds. the theologians' cosmos and the psychologists' psychocosmos, not just the physicists' verse. The answer to the containment riddle is that we who create the universes occupy the unknown universe. We, the image makers, occupy the universe. Our images are the universes we often mistakenly believe we live in. Each universe contains not life and mind, but the physical representations of life and mind, such as wildflowers and brains. The world of matter contains the body and brain, but is not the agent that contains the world of matter, which contains the body and brain. It is impossible to contemplate the spectacle of the starry universe without wondering how it was formed. Perhaps we ought to wait and not look for a solution until we have patiently assembled the elements. But if we were so reasonable and curious without impatience, it is probable we would never have created science, and we would always have been content with a trivial existence. Thus, the mind has imperiously claimed this solution long before it was ripe, even when perceived in only faint glimmers, allowing us to guess a solution rather than wait for it. Henri Poincaré, French mathematician, 1913. The physical universe contains only physical things controlled by natural laws. Is the law of natural selection a physical law? Since the time of Charles Darwin, many sons have claimed that we cannot prove that fossils of various forms are linked by evolution and natural selection, which is unfounded speculation. But the law of natural selection is as physical as gravity. The theory of natural selection requires three components: an interbreeding population, genetic variations among the population members, and a selective environment that causes differential survival. Those differences that enhance survival become dominant in the population. And the species, therefore, changes, evolves, as it continually adapts to a changing environment. We have everyday proof of the effectiveness of natural selection. Widespread use of antibiotics, such as penicillin, has decreased their potency through the natural selection of more resistant populations of pathogenic bacteria. Timelike edges pose problems that are more philosophical than physical. A Big Bang universe has a beginning, and has, therefore, a timelike edge. If this universe collapses back to a Big Bang, it has two timelike edges, a beginning and an ending. These cosmic time edges are presumably not cliff-like as in the Stoic universe or wall-like as in the Aristotelian universe, but more like the gradual fading of the medieval edge. The physical world, with its orderly historical sequence of events in cosmic time, possibly dissolves into disorderly metrical chaos at the beginning and the end. In truth, we do not understand time-like cosmic edges, perhaps because we do not fully understand time. Insofar as time, like space, is physical and part of the physical universe, we can say that physical time is contained within the physical universe and cannot extend outside. So we believe time cannot exist before or after the universe. Despite these remarks, there is a way in which we talk sensibly about what happened before the beginning of our universe. Suppose that our universe is the offspring of another physical universe, reproduced either spontaneously or deliberately by intelligent life in the parent universe. Then, in that sense, we can talk of what happened in the parent universe before reproduction. Joe Rosen at the University of Central Arkansas has shown self-generating universes and many worlds, that the offspring universe can reproduce the parent universe. Thus, parent and offspring universes form a cosmic unity that is self-creating. Universe X creates Universe Y in X's time, and Universe Y creates Universe X in Y's time. Contained creation is different from uncontained creation. Contained creation is the emergence of something previously non-existent at a specific time and location in space. Thus, examples include the creation and annihilation of particles, the creation of a flower, and the birth of a child. Uncontained creation refers to the timeless and placeless creation of the universe. When people talk of the creation of the universe, they often have in mind a creation, which is a wrong way of looking at the subject, and are misled into asking, what came before the creation of the universe? Thomas Huxley, 1825 to 1895, a famous biologist and champion of Charles Darwin's theory of natural selection, wrote in 1869 for the first issue of the science journal, Nature. It seemed to me that no more fitting preface could be put before a journal which aims to mirror the progress of that fashioning, by nature, of a picture of herself, in the mind of man, which we call the progress of science. An adequate cosmology will only begin to be written when an adequate philosophy of mind has appeared. And such a philosophy of mind must provide satisfaction both for the motives of the behaviorists who wish to make mind material for experimental manipulation and exact measurement, and for the motives of idealists who wish to see the startling difference between a universe without mind and a universe organized into a living and sensitive unity through mind properly accounted for. Edwin Burt, The Metaphysical Foundations of Modern Physical Science. Human sciences face an impasse because their central concept of the self is transcendental. G. Stent, Limits to the Scientific Understanding of Man. At the roots of all knowledge lies the containment riddle, wherein the image is the image maker. The containment riddle has haunted philosophy in various guises, and now it haunts physics. Leon Rosenfeld, in Niels Bohr's Contribution to Epistemology, explains how, in the early days of formulating quantum theory, Bohr was very much impressed by Paul Müller's The Tale of a Danish Student. The student is perplexed by problems in epistemology, the study of the validity and limits of knowledge. Man divides himself into two persons, one of whom tries to fool the other, while a third one, who in fact is the same as the other two, is filled with wonder at this confrontation. I don't know which ego is the real one to stop at, for as soon as I stop at any of them, another ego stops at it. My head gets all in a whirl with dizziness, as if I were peering down a bottomless chasm, and the end of my thinking is a horrible headache. In Mind and Matter, Erwin Schrödinger wrote, "Without being aware of it, we exclude the subject of cognition from the domain of nature that we endeavour to understand. We step with our own person back into the part of an onlooker who does not belong to the world, which by this very process becomes an objective world." Schrödinger continued, "A satisfying picture of this world has only been reached at the high price of taking ourselves out of the picture, stepping back into the role of a non-concerned observer." Schrödinger then turned to religion. Can science vouchsafe information on matters of religion? Can the results of scientific research help gain a reasonable and satisfactory attitude towards these burning questions that sometimes assail everyone? Some of us succeed in shoving them aside for long periods. Others, in advanced age, have satisfied themselves that there is no answer and have resigned themselves to giving up looking for one, while others again are haunted throughout their lives by this incongruity of our intellect, also haunted by serious fears raised by time-honoured superstition. I primarily refer to the questions about the other world, life after death, and their associated aspects. In Men Like Gods, H.G. Wells introduced the idea of parallel universes occupying what might be called superspace. Normally they remain isolated, but Wells and several more recent science fiction writers assert they occasionally make contact. Recent theoretical developments have also enlarged the notion of containment to embrace many universes as self-contained members of a super-universe. Andrei Lind, a Russian physicist, treats the universe as an eternal self-reproducing multiverse in which universes spontaneously generate new universes. Consider an ensemble of self-contained universes, covering all possible values of the fundamental constants of physics. Suppose all these universes are virtual. They all exist in potential form, and each only becomes real by observation, by conscious life. Because each is self-contained, the only possible observations are by internal forms of life. Thus, only those universes are real, and the fundamental constants are compatible with the existence of life. What happens in a universe like ours that passes through an early lifeless stage? In the early stage, no conscious life exists to observe. Does it exist? Presumably, it evolves in a virtual state and becomes real through observation when conscious life exists. This seemingly weird picture of virtual potential versus real, actual, is common in the theory of quantum mechanics. A wave function consists of many evolving, parallel, virtual states, all potential candidates for a final observed state in the real world. The anthropic principle says the universe is as it is because we exist. The theistic principle says it is because a supreme being created it for living creatures. According to the first principle, an extra cosmic agent determines the cosmic design. According to the second principle, our existence determines the cosmic design. The two principles are not in direct conflict, and it may be argued that the first encompasses aspects of the second. Consider an excited atom in which an electron transitions from an initial state to several permissible states. The actual final state is unpredictable, only its probability. Hugh Everett proposed 1957 that during such a transition, the universe splits into separate universes, each containing all permissible states. Thus, from each atom, many new universes are created each time a transition occurs, and these universes are identical, except that in each one the atom is in a different final state. A human being, composed of many quantum transitions, continually splits into numerous beings occupying different universes, each in a slightly different state and following a different history. Could the solution to the dilemma of indeterminism be a universe in which all possible outcomes of an experiment actually occur? Bryce DeWitt, Quantum Mechanics and Reality. Why not apply this idea to free will? When a person must choose between two options, does the universe split into two or more universes to accommodate all choices? In this way, we solve the conflict of free will and determinism. Rigid determinism operates in each separate universe, but a person enjoys complete free will by moving from universe to universe. All universes are virtual, except for the one the person occupies, which is the only real universe. We demand that our universes be rational and deterministic, even at the cost of creating a bizarre many-worlds picture. My preferred view is that at each decision, the branching universes are virtual except for the one that contains consciousness. Thus, free will reigns supreme, and determinism dwells in the shadows. Alternatively, free will belongs to the universe, and determinism, as conceived by the human mind, belongs to it. We do not know what consciousness is except that it is not part of the physical universe. Kurt Gödel, in 1931, showed that mathematical systems are not fully self-contained. In a self-consistent logical system, free of internal contradictions, statements can be formulated whose truth is undecidable. When the system is enlarged with additional axioms, the previous statements of uncertain truth can be proved true. However, the enlarged system contains new undecidable statements that can only be proved true by making the system larger. One conclusion is that the mathematician is inseparable from mathematics, just as the cosmologist is inseparable from cosmology. For a discussion of Gödel's ideas, see Gödel's Proof by Ernst Nagel and James Newman. What is the name of this book? By Raymond Smullyan. Scientists have answered some questions beyond reasonable doubt and have stitched these findings into a compelling, if not terribly detailed, map and history of existence. John Horgan, The End of Science. Is a final theory of the physical world possible? It has been suggested that string theory offers the prospect of a final theory. String theory attempts to unify gravity and quantum mechanics, so that subatomic particles consist of tiny strings with various vibration modes. In Dreams of a Final Theory, Steven Weinberg writes, "Our present theories are of limited validity, still tentative and incomplete. But behind them now and then, we catch glimpses of a final theory, one that would be of unlimited validity and entirely satisfying in its completeness and consistency." Against the modern concept of a final theory, we may contrast the medieval principle of learned ignorance. In his work On Learnt Ignorance, written in 1440, Cardinal Nicholas of Cusa argued that the more we know, the more aware we become of our ignorance. This form of enlightened ignorance he called learned ignorance. The darkness of unlearned ignorance disperses, and the brightness of learned ignorance grows with knowledge and wisdom. He wrote, "No man, even the most learned in his discipline, can progress farther along the road to perfection than the point where he is found most knowing in the very ignorance that characterizes him. And he will be the more learned the more he comes to know himself as ignorant." One might dare to hazard that glimpses of a final theory have frequently occurred in history, particularly when the current universe was ripe for change. Consider the unlearned, unaware of their ignorance, who think they know everything. As knowledge increases, ignorance decreases. But this kind of ignorance, unlearned ignorance, is no more than the lack of knowledge. With knowledge comes awareness of ignorance, learnt ignorance. And the more we know, the more aware we become of what we do not know. Edward Harrison, Masks of the Universe. From the heroic age of Greece until modern times, we see the development side by side of two views on the nature of space: dressed space and undressed space. Space as a void, undressed, existing in its own right, independent of the things it contains, was initially a lofty abstraction many could not take seriously. It seemed more natural to think of space as dressed and made real, with a continuous covering of material and ethereal substances. Aristotle, who believed in dressed space, regarded the notion of a vacuum as nonsense, and said that a vacuum is nothing, and what is nothing does not exist. These beliefs enabled him to argue in favor of a finite universe. The ether, the fifth element, ended at the sphere of fixed stars. Beyond the sphere of stars, there could be no space because there was no ether. At first, this was the view of scholars in the Middle Ages, who later succeeded in extending space beyond the sphere of fixed stars by inhabiting it with God. It was also the view of René Descartes, and the Cartesians hold similar views, who extended space indefinitely by suffusing it with tenuous and continuous matter. Numerous continental scientists and philosophers in the 18th and 19th centuries clung to the Cartesian view. But experiments with air pumps in the 17th century convinced many other scientists, particularly the Newtonians, that space exists without material covering. The Cartesians resisted such evidence and argued that isolated specks of matter surrounded by voids cannot exist because space is illogical, and matter must always be continuous, however low in density. Matter exists everywhere, for if there were no matter, there could be no space. Aristotelian beliefs, in modified forms, persisted until the early 20th century. Even if empty space exists by itself, many think that space is still a sort of nothing, lacking substance and possessing only extension. Elegant equations of the electromagnetic field with which James Clerk Maxwell unified electricity and magnetism in the 19th century showed that waves of light travel at finite speed. All electromagnetic waves, from radio to X-rays, travel in empty space at the universal speed of 300,000 kilometers per second. As we know, sound waves travel in the atmosphere, consisting of air undulations. How can waves of light in empty space consist of undulations of emptiness? In response, physicists filled the universe with a subtle luminiferous ether supporting light propagation and all other electromagnetic waves. The advent of special relativity helped to shake off the Aristotelian heritage. And nowadays we think in terms of the propagation of electromagnetic fields and see no need for an ether. An undressed space, a continuum that exists in its own right, absolute and independent of all contained things, is an abstract idea that originated with the ancient atomists. Accompanied by the idea that forces can act at a distance, it later became the master concept of the Newtonian universe. In the 20th century, undressed space developed into the space-time of special relativity. Then, with the rise of general relativity, space-time became, again, dressed with dynamic geometric curvature and the virtual states of the vacuum. The algebra connection. Descartes combined geometry and algebra into analytical geometry. He used coordinate systems in which the position of a point in three-dimensional space is specified by the values of the three coordinates x, y, and z. Ancient Egyptians used two-dimensional grids or graphs for land surveys, while others in later ages used them for map-making. Scholars at Merton College in Oxford also utilized them for calculations during the late Middle Ages. Space and time. Nothing puzzles me more than time and space, yet nothing troubles me less. Charles Lamb, in a letter, 1810. Scholars at Oxford and Paris in the 14th century made great strides in clarifying our notions of space, time, and motion. They invented diagrams combining space and time in their studies of motion. Later, in the 17th century, the Cartesians and Newtonians established scientific pre-relativity concepts of space, time, and motion. Mathematicians in the 19th century studied the theoretical properties of multidimensional spaces, and Charles Hinton, in 1887, advanced the idea of time as a fourth dimension. Then came the relativity theories in the early 20th century that indissolubly combined space and time into a space-time continuum. We clearly understand space. It encompasses everything around us, extending outward and containing visibly distributed objects. Distance intervals span it, and we measure it directly with meter sticks in units like meters. Time is not basic because we cannot objectively observe bodies distributed in it, or directly observe with the five senses intervals of time, such as seconds. We seem to experience time intervals subjectively and cannot objectively observe them. The impression is that all our experiences are of two kinds: objective things, trees, clouds, and mountains, that are diversified in space, and subjective things, sensations, emotions, and ideas, that are diversified in time. Somehow these opposite experiences combine to form our phenomenal world and the physical world we theorize about. The nature of time is a perplexing subject that provokes endless philosophical discussion, and the words of St. Augustine of Hippo in the 5th century still strike a responsive chord. What then is time? If no one asks me, I know what it is. If I wish to explain what it is to him who asks me, I do not know. The time that we experience as human beings, the time that devours all things, according to Ovid's metaphor, is not quite the same as that used in science. Science simplifies the time we experience into a continuous one-dimensional space that conforms to the Hausdorff axioms. We must not be too surprised if physical time lacks some of the characteristics of the time that we experience. Usually we regard the neglected characteristics as psychological or metaphysical. The fourth dimension. Physics seizes time, strips away many of the characteristics ascribed to it in everyday life, and makes it akin to space. Our physical world has become a four-dimensional continuum that decomposes into a three-dimensional space and a one-dimensional time, stretching from the past to the future. The restless world is in a state of continual change. At any instant in time, there is one distribution of things in space. Then, at a later instant, there is another distribution. Hinton initiated a revolution in our understanding of the world around us, when he showed that its continual change can be tamed and made orderly by displaying it in a joint space and time diagram. Time has the properties of a one-dimensional space, said Hinton, and past, present, and future, events, form a continuous sequence in much the same way as the points of a straight line in space. Drawing three-dimensional figures on a two-dimensional sheet of paper is not always easy. Drawing on a sheet of paper four-dimensional figures with time included as the fourth dimension is even less easy. Some might say impossible. Frequently in pre-relativity space and time and relativity space-time diagrams, only one of the three dimensions of space is shown. In his diagrams, Hinton used two dimensions of space with time as an extra dimension, perpendicular to space. In space and time diagrams, a point represents an event, such as the flash of a firefly or the blink of an eyelid, and happens at a point in space at an instant in time. A line, called a world line, represents something that endures, such as a stone or an atom, and occupies a position in space at each successive instant in time. Of paramount importance is the fact that nothing changes in a space and space-time representation. Nothing ever happens. We have tamed the restless world by displaying it frozen throughout space and time. We display everything as it was, as it is, and will remain in a world devoid of tension. A space and time diagram remains unchanged, as the use of time only occurs once. The frozen four-dimensional world in which time is one of the dimensions was dubbed the block universe by the philosopher William James, who emphasized the complete absence of change in a space and time world. The four-dimensional world of space and time is fixed and unchanging. We must refer to all its regions in a common tense. In a tenseless world, it is wrong to say that an event has happened, another is happening, and yet another will happen, for all are present together. It is also wrong to say that a body moves along a world line from the past to the future, for the body exists at all segments along its world line. We must exercise caution, and remember that the four-dimensional world already embodies time, rendering its use irreversible. If we make a mistake and say that a particle moves along its world line, we are confronted by the question of the speed at which it moves through time. This compels us to invoke a second time, and having admitted the possibility of movement through time, we must decide at what speed the particle moves through this second time. Motion through time opens up the prospect of serial time, consisting of an infinite regression of timelike dimensions. We avoid this absurdity by realizing that space-time has no physical changes. The arrow of time. World lines do not have arrows attached to them pointing in the direction of the future. In space-time pictures, it is difficult to see what determines the past and the future. When a space-time picture is turned upside down, little or nothing in the picture prevents us from relabeling the new top as the future and the bottom as the past. Past and future are labels that often have no intrinsic space-time meaning. Yet obviously a time-reversed universe is completely different. Life begins in the grave and ends in the cradle. Cool objects grow hot, candles and stars absorb radiation, and everything is in a topsy-turvy state. Presumably, such time-reversed worlds lack life and are ruled out by the anthropic principle. Most of the fundamental laws of physics fail to distinguish between the past and the future, and are said to be invariant in time reversal. The motion equations of bodies and many laws of microscopic physics are reversible in time. Their effect remains the same when the space-time picture is turned upside down and past and future labels are interchanged. Thus, two particles come together, interact, and move away. In the time-reversed picture, the same thing happens. Two particles again come together, interact, and move away from each other. Their motions and interactions are time-reversible if they can be displayed graphically. Like our spacetime diagrams, our physics equations use a spatially defined form of time with no intrinsic direction. Even the equations that govern the propagation of light are time-reversible. According to experience, absorbed light arrives from the past, and emitted light departs for the future. When the spacetime picture is turned upside down and past and future are relabeled, light arrives from the future and departs for the past, contrary to experience. Electromagnetic theory does not forbid this bewildering situation, and nothing in the spacetime picture says that light rays must propagate only into the future. Time has properties that, not only in life but also in the laboratory, cannot be entirely spatialized. The flow of heat. Thermodynamics is a branch of macroscopic physics devoted to studying all aspects of heat. The first law of thermodynamics deals with the conservation of thermal and other forms of energy in dynamic systems. The second law deals with the time reversibility of thermal systems. Strictly reversible systems are ideals that never exist, but enable us to perform simple calculations. Non-reversible systems are the real world in which heat is always lost at every stage. Reversible systems have constant entropy. In the real world, entropy always increases, while energy, although always conserved, assumes less and less effective forms. The flow of heat from hot to cooler regions is not time reversible, because entropy would decrease. No scientist would dream of contradicting the second law of thermodynamics by saying that heat flows from cool to hot regions. A mug of coffee on my desk gets cooler in the direction of the future and hotter in the direction of the past. And in the process, entropy increases. Total energy remains the same but is less accessible, and this scenario is another way of saying that the entropy has increased. If this did not happen, then you and I would not exist. The laws of thermodynamics that govern the mug of coffee and its environment are not time reversible. And yet, strange to say, the laws that govern the behavior of the individual particles that constitute the mug of coffee and its environment are time reversible. Heat continues to flow from hotter to cooler regions when the direction of time is reversed in the equations that control individual particles' microscopic motions and behavior. It seems that the collective behavior of many particles acts as an arrow of time, whereas the behavior of individual particles lacks any arrow of time. Let us try to understand in an elementary way what happens in the space-time picture when heat flows from hot regions to cooler regions. We can regard heat, in this case, as an agitation of particles. The hotter the particles, the more agitated their motions. Agitated particles move about and have wavy or crinkled world lines, and crinkled world lines communicate their agitation by collisions and other interactions with neighboring and less agitated world lines. Hot, or crinkled, world lines, surrounded by cooler, less crinkled world lines, are cooler in the future direction. This is another way of stating the second law. If shown a space and time diagram with many crinkled world lines, you immediately know the past and future. The agitation of isolated individual particles is unaffected by time reversal, but their collective behavior, the spread of agitation from hot world lines to cooler world lines, is governed by the second law of thermodynamics and is not time reversible. Single particles are time reversible, but systems of particles are not. It is like hanging a picture on a wall. If you look closely at individual dabs of paint, you will never know which way to hang the picture. You have to stand back and look at large areas of many dabs to determine the right way to hang the picture. The universe consists of numerous many-particle systems, for example, living creatures, planets, stars, and galaxies. And most scientists believe that the arrow of time is determined either partly or fully by the collective statistical behavior of these many-particle systems. Over time, the organized energies of these systems become disorganized and dispersed, and their states of order tend toward disorder. In trillions of years, when all stars have died and all systems have attained their lowest accessible energy levels, it will be difficult to determine the direction of time. In our universe, where matter is distributed irregularly in the form of stars and galaxies, we see energy continually cascade into dispersed states of less accessible energy and are provided with a cosmic arrow of time. This raises the question: is there no arrow of time in a perfectly uniform universe without irregularities? Such a universe might be expanding, and the change in its density will identify the past and the future. But how would we know that it is expanding? It might be contracting, and the higher density lies in the future and not the past. Thomas Gold of Cornell University has argued that the universe gets its sense of time direction from its expansion, and the future always lies in the direction of diverging world lines. In this case, it is unclear what happens if the universe ceases to expand and begins to collapse. Our everyday experiences make us acutely aware of the now as a moment or segment of time. We, but apparently not Aborigines, Mayans, Hopi, and many other societies, imagine time as a river. Our boat, now, drifts on the river of time, gliding past a changing landscape, with the future always approaching and the past receding. Alternatively, we can think of the now as a wave of vividity that divides the known past from the unknown future. We are aware of transience, of things becoming, bursting forth into actuality, and then fading into a limbo of memory. Our awareness seems like an asymmetric wave of vividity advancing into the future, having an intensity that is almost zero ahead, rising sharply to a maximum at the present moment, and then falling off slowly into the past. Our languages embody a mixture of primitive and sophisticated metaphors concerning the nature of time, and their conflict leads to confusion and paradox. Amidst this confusion, we discuss being and becoming, free will versus determinism, and the arrow of time. So far, we have failed to harmonize the discordant concepts of temporal continuity, states of being, with transience, states of becoming. We only need to ask at what speed the now moves through time. At what speed does our boat drift on the river of time? To realize that we still do not understand time. Each of us in space-time is a world line, a bundle of interwoven world lines like the fibers in a rope. This representation, however, does not explain the now that moves up the world line from the past to the future. Hermann Weyl, 1949, wrote, "The objective world is, it does not happen, only to the gaze of my consciousness, crawling upward along the lifeline, world line of my body, does a section of the world come to life as a fleeting image in space, which continually changes." A simple model of this process consists of a space-time diagram of world lines, over which lies a cardboard sheet having a horizontal slit. The slit, which exposes a thin slice of space-time, reveals a three-dimensional world of space. The world lines passing through this space are particles occupying points in it. As the slit moves upward, we see the particles moving around in space. Fully spatializing time leaves us unable to physically explain our experience of transience in a constantly changing world. If the now moves upward along a world line, at what speed does it move? Must we invent a second time to account for this motion in time? If this second time is spatialized like the first, then we need a third time and so on, and we have the frightful prospect of serial time. If time is fully spatialized, we encounter the paradox of motion, no matter how many dimensions we assign to it. Transience. Scientists, confronted with how we move in time, tend to dismiss it as a metaphysical and not a physical problem. Many are inclined to the view that it is a psychological illusion. However, such views never seem convincing, and can be dismissed with Gerald Whitrow's words, "How do we get the illusion of time's transience without presupposing transient time as its origin?" The Natural Philosophy of Time, 1980. Whitrow also makes the perceptive comment, "Time is not itself a process in time." The physical time incorporated in space-time is a refinement of Newtonian time, and Newtonian time, which is still used in sciences apart from physics, is a refinement of colloquial time used in cultures of European origin. Many people believe that space-time incorporates real time and that an awareness of transience is a non-physical peculiarity of living creatures. This view revives the Parmenidean doctrine according to which the real world is changeless, and our transitory experiences are illusions. Which is the real thing, the idea or the experience, opens the endless discussion. If ideas derive from experiences and experiences are illusory, how can ideas be more real than experiences? The real problem is, if living creatures are nothing but bundles of world line fibers in spacetime, how can world lines have an illusion of transformation when nothing in spacetime changes? How can we hope to explain the illusion of transience without presupposing